Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 37. A brief recap of what we did in the last lecture. We were talking about the different geometrical aspects of machining, particularly in the machining zone, where you could actually correlate between the uncut chip thickness and chip thickness with respect to the various angles that were formulated, particularly the shear plane angle, the friction angle, the rake angle of the tool that the tool makes with the vertical, etc. Today we are going to look at again the force analysis aspect, and for that we had just started covering the dynamics of the chip formation process, particularly as the chip sort of comes out of the material and separates from the primary workpiece material. It is treated as a rigid body and there are lot of forces acting over it, particularly from the rake face of the tool or from the shear plane or from, let us say, the tool to the workpiece, and all these kind of balance together as a common resultant. So I am just going to recap that portion before starting again. So the assumptions that we make have been brought forward, as I earlier mentioned, by theory proposed by Ernst and Merchant, and the assumption that was made was that idealized shear plane model is good enough to predict the approximate value of power consumption of the metal cutting process or the metal chipping process, whatever you may record it as. And the assumptions also were that the chip above the shear plane was considered to be a rigid body, moving with constant velocity, and in this respect we had actually drawn a diagram which talks about the chip formulation process. Let us say this is the cutting area, the cutting zone, and there is a chipping action which happens over this particular plane. Let us say this particular plane is formulating or is responsible for formulating the chip, or this is the shear plane. This is the chip, the workpiece, and the tool makes an angle alpha with respect to the vertical axis here, and which is also known as the rake angle. So I am just going to separately show the tool face, just in case, although they are sort of meeting with respect to the chip, but we are showing it separately because of for the sake of convenience of the force analysis that would be projecting. So this angle right here that the tool face makes with respect to the vertical is the angle alpha, and we also know that this plane angle here right here is phi, and basically if we consider the chip to be a rigid body, meaning thereby that two different points on this body will not have a positional variation with respect to each other as a function of time. So it should not do any deformation, etc. So the chip should be in force equilibrium conditions, and for that the resultant of the forces acting on such a rigid body, and let us just write this down here, that the resultant of forces acting on such a rigid body from the rake face of the tool and the work surface along the shear plane should balance out. So, I call this R dash for example, should balance out. So, only if there is a force balance it can be treated as a rigid body, and basically we are also talking about a constant velocity case. That means, the chip velocity here v is treated to be invariable with time. So, there should not be any acceleration component involved and the forces should be in just an equilibrium with respect to each other. Also, we assume the cut velocity in this case to be constant. So, therefore, the force that the tool applies on the workpiece and that whatever the workpiece applies back as a resultant, they should also be equal and opposite to each other. So, these are some of the presumptions which are made in order to analyze the merchant circle or the force circle that comes in these three components, that is the chip, the workpiece and the tool. So, the total of the forces acting on the chip by the tool is basically also a function of the normal reaction that the chip would have by virtue of its curl or by virtue of its pressure that it imposes on the top of the tool surface, and the frictional force which happens because the chip is moving in a certain direction. Let us say the chip is moving out in this direction v, and so therefore, there has to be an opposite frictional force F which acts on this particular chip opposite to the direction of its motion over the rake face. Okay. So, a normal force N, which is because the chip has applied certain pressure on the top of the rake face. Obviously, you are trying to scribe it out, meaning thereby that you are trying to take it to a position along the shear plane, so that earlier whatever component it had is now deformed, and because of the deformation process. So, there is a resultant force which acts because of both these forces, and this can be treated as the resultant force R because of the friction that the friction and the normal reaction provided by the tool face on the chip surface. On the other hand, on the contrary, you have a resisting force opposite to the again the shear direction of the chip. So, the shear is along this plane particularly. So, obviously, the resistance that would come to the workpiece or the resistance that would come as a result, the resistance force from the workpiece to the chip that would come as a result of the chip fragmenting from the workpiece will have Fs, the shear force in the direction of the shear plane, and also it will have a normal force Fn, which is actually opposing the force that the chip is facing on its mating face with the tool surface. So, there is a normal reaction and there is again a shear force, and the resultant of these two I consider to be R dash, where R dash can be said equivalent to be minus R. That means, it is equal and opposite to the resultant reaction of the chip by the tool face. So, the chip being a rigid body, now you have these two kind of forces, one generating from the shear plane right about here and one generating from the tool face right about here, and it is a constant velocity situation. There is no accelerative component which is there. So, we can consider the summation of all these forces to be equal and opposite to each other, and the chip exists as a rigid body. We are not assuming deformation in this particular case, because at least just after the formation process or after the chip has started to peel off, that is the case that we are evaluating. Obviously, there would be deformation because the chip was earlier the workpiece which was extended by this dotted line here, which is actually rotated in this direction to formulate what you call this chip. But we are not talking about that instance, we are talking about an instance when this formulation has taken place already and the chip has started to formulate and come out, and there we are trying to do the rigid body assumption. Okay. So, in that event the r dash and r are equal and opposite to each other, and the total force F and N which is acting as a result of the frictional and the normal reaction on the chip from the tool surface, they can also be correlated by putting coefficient of friction mu between the tool chip interface as a ratio between both the forces. Mu is the friction coefficient between tool and chip, and again we are just assuming a average friction coefficient and an average friction force. Obviously, the force distribution would vary quite a bit at this interface, because the chip may not be curling equally on the top, or the chip may not be putting equal pressure on the top of the tool face. Obviously, the pressure would be more towards the cutting zone and lesser. So, there is a distribution lesser in the outward zone. So, there is a distribution, and basically the idea that we are having here is that we report an average value of this frictional force, and therefore, this coefficient here is an average friction coefficient between the tool and chip surface. So, having said that, now we want to sort of do a force balance between whatever forces we have now outlined, and for doing that we would like to again draw this or redraw this diagram of the force, various forces which are acting on the surface of the workpiece and the chip. Let us say this is the chip being formulated, and the shear plane is represented here. We have remaining portion of the workpiece, and let us say this is all connected. So, this is the same workpiece that we are talking about, and here we have the tool. So, obviously, if we look at the tool angle, so the tool angle is between this vertical line and the tool face right about here. I would call this alpha rake angle, and what we want to do is to just slightly offset the point of intersection to the point where the reaction would obviously come. So, I am going to have a parallel axis just off shifted a little bit, just to address conveniences, and then again another plane, and across this we would like to find out what goes on in terms of all the forces. So, you have the shear force component for between this and this. Okay. So, this is F s, we can write this F s here. Maybe I will just make the F s magnitude a little bigger all the way up to here. So, this is F s, and similarly we also have a normal reaction component which is going somewhere here. So, we call this F n. Okay. Let me just clear this a little more, so that it is convenient to understand. So, here we are just extending this component all the way here. The angle here should be 90 degrees. I am just going to make this a little look like orthogonal to each other. So, this right here is F n, and there is, because of these two forces, a resultant reaction which would be applied to this particular point right about here, and this we consider to be the reaction R. Similarly, we have a component of the friction which is parallel to the rake face. So, this component of friction is in this direction parallel to the rake face. We call this force F, frictional force, and we again have another component which is just perpendicular to the rake face of the tool, and we call this the normal reaction N. Just for sake of convenience, I am going to just shift this term F n to its vector component here. Okay. So, this is F n, So, this is kind of the force diagram which gets generated because of the two resultants being equal and opposite to one another. So, having said that now, so obviously the r dash that I was talking about would come in some direction here, which is exactly opposite to the direction of the r, which is result of the summation of the forces of friction and the normal reaction of the tool face. So, by the by, this particular angle then would be equal to alpha, obviously, because it is the same as this particular tool angle, the tool angle alpha that has been represented earlier. And I would again like to just mention here that the velocity of motion of the point of engagement of the tool, which is again opposite to the velocity of the workpiece with respect to the tool, the feed velocity, that velocity also being constant, we can say that the forces that the workpiece exerts on the tool should be equal and opposite to the forces that the tool exerts on the workpiece. So, that the accelerative component is 0 now and there is a constant velocity case. This point kind of moves forward at v feed velocity equal to constant. And so, here in that event, what I would assume is that the total forces that are given by the cutting zone onto the tool are one in the perpendicular direction and another in the direction parallel to the coordinate axis system that has been shown here. So, one is obviously in this direction right about here, okay, and I call this the cutting force F c, which the tool exerts on the workpiece or the workpiece gives back as a reaction to the tool surface, and this can actually be measured by putting a small dynamometer on the top of the tool surface. And then there is another force right about here, which is actually called the tangential force. We call it F tangential, okay, which is perpendicular to the direction of the tool movement, okay, and it comes by virtue of the fact that the tool actually is grazing or pushing into the workpiece surface, and this resultant should also be the same r and r dash, so that there is equilibrium and this v can be considered to be constant. So, having said that now, so obviously at a constant feed velocity you would ensure that you provide a force equal to this F t and F c, so that this tip moves at a constant velocity with respect to the surface. But in any event, the reaction force that comes out should be balanced, so that this reaction force is in a way able to have a situation where the point of engagement moves at a constant velocity. So, this is actually overall the force diagram. I can actually draw a circle around this force diagram. And such a circle drawn is also known as the merchant circle, and this force diagram under this circle is called the merchant circle diagram. So, having said that, let us now figure out some of the angles. The angle between the shear plane and the horizontal here happens to be phi, and the angle which is actually between the frictional force and the normal reaction, mind you, mu is actually F by n, which is also equal to the friction angle, the tan of the friction angle, tan lambda. It can be represented here. So, lambda is this particular angle between F and n, F equal to n tan lambda. And having said that, we have this angle right about here, which we find out as pi by 2 minus lambda, because obviously the total sum of the total angles here in this particular triangle where which comprises of the friction force F and n and the resultant reaction R basically is 180, and this angle being lambda obviously makes this other angle 90 minus lambda. And so, basically the total angle this right here can be represented as 90 degrees minus 90 minus lambda minus of alpha, which is actually represented again as lambda minus alpha. So, this angle right here can be represented by lambda minus alpha, and you have phi, you have lambda minus alpha, you have lambda, all these different angles now defined. Obviously, if this is phi, then this should be 90 minus phi, and same this should be 90 minus phi. So, this angle must be phi then. Okay. So, you have more or less all the angles defined now, and having said that, now the force vectors Fs, Fn, Ft and Fc has certain angle based, component based relationship, and what I am now going to do is to sort of put together what are the different kind of relationships which exist in this kind of a case. So, this we will actually continue in the next module. In the interest of time, I am going to close on this module. Thank you very much.